All right, everybody. Again, this is Mr. Hayden. This is chemistry. I guess this is week 8. I get mixed up on my weeks because this is the first one, so we're going to go week 8. Week 8 chemistry. Thanks for checking me on that. Basically, what we're going to do this week, guys, is it's not really a huge. As hard as like we've been learning all this stuff that's like super complicated, all these formulas and all that. What we're going to learn now is not so much as complicated as it looks. We're going to talk about like molality and things like that, not molarity, molality. And we're going to look at basically what is like we talked about solvents and solutions and stuff like that, but what is the percentage of that in there based on its mass or based on its volume? And so we're going to go through the K12 class. I'll show you how to do that. And we'll show you how to calculate a few of them, or like one of the, basically the examples that's in there if you haven't seen it yet, and how they break that down. It's pretty straightforward. It's really not a hard concept. It's just a concept you need to know to do calculations down the road, okay? Good? Excited? Everyone excited? Everyone's excited. People are excited. All right, let's go. Okay, so the essential question, or more of the essential part of this, is define molality. And again, it's different than molarity, a little different. We want to make sure to define that, understand that idea of the concentration and volume and whatnot. That should be pretty simple. The people that are in person, they definitely need to know that, but they won't have to actually define it because we'll be looking at that basically today in class. So if you go online, you need to make sure you post that to my Dropbox inside the class to make sure you get the credit for showing up. And remember, and this is just in general, guys, this is just one of those things just to bring up. If you have obviously you have a homeroom. If you happen to have a D or an F in one of your homeroom for any class, you should see your homeroom teacher on the first day that you show up to a live session. You'll be picking up a golden sheet of paper, and on that golden sheet of paper, you'll have when you go to that live session, you're going to have your teacher sign that live session that you went there, and at the end of this, basically for me at the end of the week, you're going to turn it in and I'll turn it to the office. And so the office basically is going to start now knowing that if you showed up or not. I've been taking, obviously, attendance for my class, but they don't want it that way. They want it for homeroom. So make sure you tip your homeroom teacher, pick up that piece of paper so I can sign it if it needs to be signed. If you happen to have a D or an F in this class, okay? Just making sure. All right. So let's look at it. Now, the major concepts for this lesson, and one of them is what your essential question is. We describe 2 ways of expressing percentage concentration of a solution. So we're going to look at 2 different ones. We're going to look at volume versus volume. So example, how many liters of salt you have in liters of water? What is the percentage? Is it 25%? Is it 100%? Whatever it is. We're going to look at also mass to mass. So what is the weight? Okay, so what is the actual weight of the salt compared to the weight of the water? So we can do either one. It's basically the exact same thing, one's based in volume, one's based in mass. We're going to define molality, which you already did. We're going to go calculate molality in a solution, which is one of the things we're going to go over. So there you go. All right. So to review the concepts of molarity and mole fractions, this is just basic. You guys remember how to do the actual moles of a substance by looking at the mass most of the time. How many? Right? Help me out. What do you find? What happens? Looking at molarity, like example, like looking at water, H2O, 1 mole of water is 1 mole of water, but then if you look at what's the mass of that mole, you look at the mass of that particular mole. It's not really going over making sure you got it. Okay, so if you look at the solute, the mole fraction of the solute is the moles of the solute over the moles of the solution. So it's basically just a ratio. The fraction of the solvent. So what is the solvent over the solution? They should be, when you add them up, should equal 1. Just a review, hopefully. Okay, looking at concentration. So example, in the one little container to the left, there's going to be a 10% water, or 10% of salt in the water. Now, it can be calculated in volume, such as out of 100 milliliters, 90 milliliters is water, and 10 milliliters is salt. Pretty straightforward. It's the exact same thing. It's a percentage. On the opposite one, on the right-hand side, it could be 3% salt, 97% water. Those can completely change based on what you're doing. Now, when we did the solution solvent, things like that, when we were looking at how salt dissolves and all that other stuff, What we could have even done, if we wanted to get into this further right away, is we literally could have measured the volume of the water, measured the actual volume of salt, poured it in there, and you have the ratio right away. Or what's easier for me is not just, is how am I going to get a figure? For salt, it's kind of hard to figure out the milliliters. It's harder because it's not liquid. You could just take max. Just weigh it. Here it is. Boom, weigh that. There's the ratio. Pretty straightforward. So that's just this idea of getting a percent of the solution. Obviously, the one with 10% more salt will be a higher concentration due to the higher percentage of the solute. Makes sense. Which one would you drink if you had to drink one of them? The water with more salt or the water with less salt? Louder. People on the internet can't hear you. Less salt, right? Obviously. So you want to pick one with a ratio that's a low ratio like this. Okay. Now, when you look at volume to volume, this is really easy. I'm sorry, I don't know how to make this less clear. You literally want to write down the formula of the volume of the solute on the top and the volume of the solution on the bottom. So it's what you're putting into the substance and what the substance will eventually equal. Because it's the byproduct of both together. And that gives you the percentage. This is exactly what we saw in the other one. So if you have 10 milliliters of the solute over 100 milliliters of the solution, your percent solute is going to be a 10%. So 10% of that solution is the solute. And so far, if we have under 10 percentages, we learned this a few years ago probably. We good? Hopefully. This is the exact same thing, but looking at mass of the salt compared to mass of the solution. So you just weigh it over that. And you get the exact same type of calculation. You'll get a percent, just like the other one. You'll get 5% on this one and 2% on this one. Again, it's the exact same thing, but it's mass to mass, volume to volume. You can't go mass to volume. Does that make sense? But you can't say this much mass of this much mass of this much volume. It won't equal out. It needs to be the same terms or the same units of measure. So far, so good. If you get a hiccup here, let me know. Okay? Team two, it's like you feel like I don't understand what you're talking about. Raise your hand. I saw your hand go for a second. I was going to mess with you. Okay. So this is where the concept of molality comes in. The concept that you're looking at here, and that you should be writing down in your assumption question. The definition, and we use that as symbol small m, so don't make that mixed up. It's kind of italic m. Don't get that mixed up with mass. Okay? Italic small m. Don't get that mixed up with mass. It's a measure of a number of moles in a solution, 1 kilogram of salt. It expresses, I'm just going to read this now up here. It expresses the concentration in terms of the mass of the solvent. Be careful though. The word molarity, and that's a big M, sounds a lot like molality. But molality is measured in moles per liter. Molality is moles per kilogram. Make sure you know that. There's a difference. I put like molarity like equals like liters. Like molarity equals liters, and like molality equals kilograms. I think I've written like that down. Okay. You good? Okay, I'll give you guys a second to write that down. And some people on the internet, they're going to be writing that down as well. I'll give you a second for that. Huh? What? Peanut butter. We good? No, some people are still writing. Let's go and finish that up. Mark. I just like saying things. Okay, I think we're almost done, or pretty much done. So let's go to the next one. Okay, so let's look at this in action. So bromine, we're going to say that as the symbol Br. The atomic mass of it is approximately 80. So that's something you can look at your table and find out. So what we're going to do is we're going to take that, and if you look at the top, how many bromines do I have?
You got two.
I got exactly 2 actually. Yeah, yeah. So BR sub 2 basically means you have 2 of that particular, in this case, just this element. So you do have to make sure you calculate the mass out. So if you're telling that with 80 times 2, that's how many there are. Your molar mass is 106. That's how you can molar mass. You basically add up anything like H2O. What's the molar mass of H2O?
So,
Up top of your head. Up top of your head. That's hydrogen, which is how much? What was that weigh? Weighs 1. H2 is 2. And what's oxygen?
Oxygen's like 15 or something. So probably like 15.
16. So the molar mass is going to be 18. So the molar mass of water is 18. You just add them up. Pretty straightforward. In this case, you add them up. They're there. Good for us. Okay. Let's go to the next slide. So to be able to determine the moles of bromine, you take your 40 grams of bromine is used, and you actually have to calculate the moles that you're using. How many moles? So, for example, 160 is 1 mole of the solution. Right? 1 mole of that particular substance. So what you're doing is you're using a percent of it. You're using a quarter of it. You're only using 40 grams of it. Okay? So you understand this. And this is where some of you get hicked up on coming down with this ratio. So example, if it says that you're using 160 grams of this, how many moles am I using? 160 over 160. 160 is basically how many moles is your molar mass total. Again, whatever it says you're using, you put that on the top. Sometimes they'll say that you have 320 grams. You're using 320 grams. How many moles are you using? No. 320 divided by 160. Good. So that's where this ratio comes from up in the middle. Remember, so you'll get 0.25 moles of boron being used in this situation. Now the question comes is, how do you calculate that in kilograms? So what you have to do is you have to calculate it out. So you have calculate the molality by dividing the moles of boron by the number of kilograms to get the number of moles per kilogram. So, anyone stuck there yet? You good? You take the number of moles, the percent now, basically. So you have your 0.25 moles of boron. You divide it by how many kilograms, which is 4 kilograms. You do the math on that. And so you'll have 0.0625 moles over kilogram. That's the molality. That's why it's going to be in sub small m italicized. You guys are looking at me like you don't understand. Is it one of those, or is it you're just bored because it's so dang easy? Which one is it? Which one is it? Help me out here. The correct answer is C. All right, so let's just look at one more example. So molality of a moles of a solute over the kilograms of the solvent, and you basically do the exact same type of ratio. So NaCl, we're using, this is when you actually see the math, but we'll go over. So we have 20.4 grams of it. So right here, you need to figure out how many moles, and there are this many moles solution. You have 1.82 total, right? Yeah. Divided by, oh, did all the math for us. Good for us. This skipped a way to do it. This is when it's shorthand. You guys understand the shorthand, or do you want to do longhand? Longhand would be if you go ahead and calculate the ratio of basically 20.4 divided by 58.43, and you got your whatever it is, 0.5-ish, 0.5 something, and then you would divide that by the amount of kilograms. It's skipping a step. Does this make sense, or do you want to not do that? Either way, you get the same answer. All this did was that it puts basically what is the number of it over what it tells you, the kilogram of the solvent, and then you have to do your 1 mole of NaCl over what is 1 mole of NaCl. You have to look at literally the atomic at the periodic table and look at what the mass of Na is, and look at what the mass of Cl is, and add them up, because that's what the mole mass is going to be. Does that make sense? Give me a smiley face online if that makes sense. Of course, you guys know it. You guys are all awesome online. People in person now, they're the ones looking at me with non-smiley faces. Does this make sense or no? So, yes. We do get it. We get to learn. Yeah, good? No, or not? Not sure yet? We let me know. Yes or no? Yeah. No. Okay, good. No, good. I like it. You get it? Good. Good. Shoulders up. Good. Good. Kind of? Smiley face? Simple? Easy? Simple? No. All right. Okay, so some of the people don't get it on the in person, so that's cool. I'm just going to quickly go through this. So the very first step to find molality is you need to find how many moles of the solute you're going to have. So it's going to give you a mass of the solute, whatever it is. So if it says, I'm going to use 1 gram of hydrogen, how many moles is that? That's the question, right? I have 1 mole, so I'm using 1 gram of hydrogen. Well, how much does hydrogen weigh? 1. 1 gram. So guess what? The grams pop off, and I have 1 mole I'll be using of hydrogen in that case. What you need to take is the first thing you do is find the ratio. Your numerator becomes what is it giving me? What is the number giving to me? For example, the NaCl, is it just water only? Is it O2? Whatever it is, you need to be able to go to the periodic table, and under each one, you'll see this. That's the atomic mass, which I hopefully you remember from last semester. Then what you do is, in this case, it says Br2. So I take approximately 80, and then there's 2 of them, so times 2. So I know that in 1 mole of Br2, 1 mole, there's 160 grams. Anything more than that is a ratio of greater than 1. Anything less than that is less than 1 of a ratio. Makes sense? Does that make sense? That's fine. No, if it doesn't make sense, that's totally cool. When we get done with this, I'll do some more on the board on the room, okay? All right, so we'll continue. We'll go back over that. All right, we're going to kind of switch gears right now a little bit, and we're going to talk about ways to separate solutions. So you have a solution, it's just sitting there, and you want to get rid of it, like one or the other, okay? You want to break it apart. So, for example, if I have sodium chloride mixed with H2O, what do I do to separate it? Which is called desalinization, by the way. I can use evaporation, and we'll see an example of that. I can also use like special filters that go through it and actually hold back everything but the water. That's called desalinization. We use it to get sometimes our drinking water. So these are ways to look at it. The first one here is distillation. It is basically you're separating liquids. This is the way that you can, in theory, take salt and water, put it in a little vial, which actually I'll just bring up the vial. And the next slide is a bigger picture of that. Okay, so if you take the little vial in the middle with the little Bunsen burner hooked up to it, you take your salt water and you put it in there. You turn on the heat. What happens inside is it evaporates. It gets hot. It turns into vapor. That vapor has no salt in it. It's just water. That's what water vapor is. So the water comes up. It cools down in a little blue tube, which by the way, that's a blue tube is a metal tube with typically cold water surrounding the blue tube. And what happens is it condenses like a cloud of it. It makes rain, like a kind of artificial rain, and it drips into the beaker on the right-hand side is fresh water. You can actually do this. If you ever watch anything like Dual Survival or any of that stuff, if you have the ability to find a can and some piping and things like that, you can actually distill your own drinking water from the ocean. You can technically distill your own drinking water by digging a hole, putting a plastic bag in there, putting anything in there. This could be salt water, this could be gross, disgusting water you'll never want to drink. This also could be your own urine. You can put it in there, you can put a cup in the center of it, put another plastic bag over the top, put a little rock over the middle of it so it'll condense. It'll condense on the top. It'll actually filter to the very bottom of that rock and drip into the cup. The cup is fresh water now. You're doing the exact same thing. You're taking energy and using it to separate a solution, basically. This time it's easier because it's salt or something like that, or you can do it with urine. Urine is mostly water, but you can separate it in the same exact process. This is also a way that some people are, when you make hard alcohol, this is how they make hard alcohol. They take a solution of whatever it is. Typically it's a sugar in there, as well as like yeast, which is a bacteria that eats the yeast, the base eats the yeast, or the yeast eats the sugar, I'm sorry. It actually byproduct, or its species, it's the way, what it gets rid of is actually an alcohol. And what happens is that you distill it, the water vapor is not water, it's alcohol vapor. Then the alcohol vapor condenses in the tube just like water, and on the other side, you get alcohol. That's how they make hard alcohol. So, that's the exact same process of distillation. You know, there's the movie, it's the show Moonshiners, that's what they do. Yeah, basically what they do. It's more, a little bit less and more sophisticated depending on what you're doing. So that's one of them. Another one, I never say it, chromatography. Chromatography. You never say that. Like a few words I cannot say, I don't even try anymore. The word right there is basically as you start going through a certain substance, it'll start to separate. So example, if you, and there's actually a lab that I believe coming up that we do this. Yeah, I think
it's in the beginning of last.
Yeah, I did all my years in Extend, so I thought maybe it was coming up since we're doing this. Yeah, last year, we did this where we took some oil, we took some alcohol, then we took water, and we put ink on it, and then the ink itself is the solution. With a whole bunch of stuff in it, so colors-wise. And as the substance went through it, it separated it from one color to another color to another color to another color. That's the idea of separating the solution that way. So hopefully if you remember that lab, you remember what we did. This one right here is fractionation, or breaking down breaking things down further to get for different distinct boiling points. So this is what they would use when there's petroleum. So they'll pump oil out of the ground, and they'll actually use the system of separating it by density. And at the very bottom is the heaviest, and at the top is going to be the lightest. So if you see here from the bitumen, like that on the very far left of your screen, that's the heaviest, that's the more solid, things like that. That's like your crude oils, you know, your fuel oil. Then you have your lubricants that pop up all the way to the far right hand side where it looks like it's the clearest, and it's actually gasoline you put in your car. Yeah, well, fracking, what they do is a concept where they do that, but what they do is they basically destroy a whole area that has a bunch of oil inside of it, and they basically like suck the oil out of it, and it kind of can leak and seep and ruin the environment if it's not done right, and it kind of distracts. It can break it, pull down, it can destroy the environment, things like that if it's not done right. But this concept is more like, you know, like the oil refineries? That's what they do. They take an oil and they refine it from big, like the thicker, like the oil you put in your car, like the actual oil like for the engine itself, so it stays lubricated and things like that. That's going to be over here towards the lubricating oils, more to the left. The ones you're going to use to burn and actually use fireys with a higher octane for your actual gas. That's to the right. And there's different octanes. Like there's 85 octane, there's 87, 91, or 89, 91. All those are various rates of that. So certain engines can only take 91 octane. And I knew people back in the day that had high performance, like Mustangs, and it only took like, they go to special places where like 102 octane. It was ridiculous. And they were like more expensive and all that stuff. Now you can find 85 octane, and some cars run on that, and they're actually usually about 20 cents less per gallon. All right, this one's probably the easiest. It's basically straight up osmosis. the concept that there's a barrier that only allows certain size molecules to pass through it. The smaller ones typically will pass through, hence the green ones, and the purple ones are left behind, and that's how I get separated. You can also use this when we're desalinating water, because you can push water through it and allow for the salination or the salt to stay back, and you get water left behind. It's called desalination, and it's something that, in theory, they think will be better, like eventually down the road, because we can just take the ocean and make it into fresh water. And that way you don't have to worry so much about how much rain there is, and how much is in our aqueducts, and all this other stuff. So we can get it from the water. Right now, though, it takes so much energy to separate salt from water, it's just not economical. Like, you wouldn't buy it too expensive, because the water itself is too expensive. All right, so any questions online? If not, go ahead and have a good rest of your day. I'm going to probably break down a few more things inside of the concept of the molarity and things like our molality. See, I need to do stuff. Make sure you don't. And so you can go ahead and take off, and make sure you put the essential questions in the Dropbox. Have a good day.